Hi everyone, welcome back to our discussion of synchrotron radiation from a polar distribution of particles. In the last few lectures or last few videos, we've looked at the radiation spectrum from a polar distribution of particles, and we've determined that for a distribution which looks like gamma to the minus p in the Lorentz factor, we get a broken power law spectrum which has an omega to the 1/3 tail, an omega to the 1 minus p over 2 segment, and then an exponential cutoff. This, strictly speaking, is the emissivity or the emission coefficient of the region of space that is producing synchrotron radiation. This tells you how much light that volume is making. It actually doesn't, there's an additional step we need to do to figure out the radiation that we receive. And that has to do with the aspects of radiative transfer. So if this entire region of space is transparent, then the light that we will see is indeed going to be the sum of all of this radiation from along the line of sight. But if it is not fully transparent, then the radiation starts interacting with the particles and the particles start absorbing the radiation and gets a little more complex. And that is the subject of this video. We're going to talk about synchrotron self-absorption. Before we get into the details of self-absorption in the context of synchrotron radiation, I wanted to remind us a little bit about radiative transfer, because we'll be using, I'll be throwing out various emission and absorption coefficients, and I'd like you to be able to put that into context as to how you might actually use this if you wanted to solve this problem in an astrophysical situation. And now again, depending upon where you're coming at into these videos, you may have studied radiative transfer, you may have looked at the radiative transfer equation, you may even have solved that in a few specific examples, a few specific cases for different types maybe of radiative processes, or you may not be familiar with it. And so in either case, I'm going to do a quick recap. And so the idea behind the radiative transfer equation is that we are interested in the evolution of intensity. So what do we mean by that? Let's say we have a region of space and it is making light, and we are observing it from some distance. Then as light propagates through this region of space, the amount of energy content of the light will change. So the energy content will change because processes like synchrotron radiation could add to the amount of light there is propagating in that direction. Or there could be particles sitting there scattering off the light into different directions, or absorbing the light and re-radiating it at different frequencies. So there could be various processes inside this region of space changing the properties of the light. So when by properties I mean the amount of energy, the energy as a function of frequency, the direction the light is propagating. So usually astronomers like to keep track of this through the quantity called the intensity, or the specific intensity. I'm not going to define specific intensity and its units and dimensions, and those discussions are given quite well in the first chapter of Rybicki and Lightman. And so if you're not familiar with intensity, I'd recommend having a look at that and then returning to this video. On the other hand, a lot of the discussion that we're going to do doesn't necessarily require a lot of detailed understanding of the concept of intensity. So for now, you can also proceed with the understanding that the intensity, which let me define, is the energy per unit volume, per unit frequency, per unit solid angle that is propagating along a given direction. As long as you just keep in mind that intensity is just how much light is going that way at some frequency, then that's really all you will need. So I'm just going to remove this I and indicate to us how this intensity might change. So as this light ray propagates through this volume of space, what might happen? So the radiative transfer equation just tells us how the intensity changes as a function of path length through a medium. And so that is the left side. The right hand side is all the processes that contribute to this, right? So you could add to this intensity, and the addition of intensity just comes about by processes making light. And a typical example is synchrotron radiation, but it could be anything. And so this is where you put in the emission coefficient. And by the way, I'm putting in subscripts nu for frequency, but really nu and omegas are of course related through their 2 pi, so omega is 2 pi nu. And traditionally, this equation is written in I nu rather than I omega, but you could write it as I lambda if you like, right? So that's up to you. So I'm writing it the way it's traditionally written and how you might find it in books. So how does the intensity change as the light ray propagates? Something adds to it, processes like this radiation, or you can also remove radiation. So similar processes like synchrotron radiation can actually remove light because the laws of physics are time reversible, and so the same thing that makes light can just absorb the light back, or you can scatter it, various such things. So for absorption, the corresponding coefficient is called the absorption coefficient, and this is multiplied by the intensity itself to indicate that some fraction of the intensity is removed as the light ray propagates. And this is a differential equation. These quantities j nu and alpha nu depend upon space, may also depend upon time, and so as the light ray propagates, we need to integrate this over the path length. And of course, you can see that on the right side we have the intensity itself. So this ends up being an integral differential equation where the solution is part of the integration, the differential equation itself. And there are formal solutions of this radiative transfer equation, which we'll not go into today, but it basically involves the use of integrating functions. But for now, I'm just going to write this in another form, which you may be more familiar with. And to do that, what we do is we divide both sides by this absorption coefficient, which just tells us how much light is being removed. And we'll go into the details of this in a second. And so we write di nu by alpha nu ds is j nu over alpha nu minus I nu. And then traditionally, this quantity alpha nu ds is called the optical depth d tau nu. So this is a dimensionless quantity. It turns out alpha has the same dimensions as length inverse. You can check from here. And so this is a dimensionless thing that tells you how opaque the system is. So for high optical depths, higher taus, the system is fairly opaque. And for low optical depths, low tau values, the system is what is called optically thin, or on the transparent side. And then this quantity, j nu over alpha nu, this has a name. This thing depends upon the properties of the emission, the thing that's emitting and absorbing. It may be the same process, may be different processes. Here, typically, this is per process, right? So you write a differential equation per process, and then you can just kind of sum those differential equations together. And so for any given process, the ratio of its j to its alpha is called S nu, the source function. And the details of why it's called the source function are not really relevant here, but you will actually see as we go through the synchrotron case how this makes sense, and allude to that shortly. So this differential equation can then simply be rewritten as di nu over d tau nu is S nu minus I nu, where S nu is the source function of the process that's emitting and absorbing, and I nu is the intensity itself, and that's the quantity we're typically interested in. Now, so why is this? And this is called the radiative transfer equation, and it's discussed in a fair bit of detail in Rybicki and Lightman. So the reason this source function is such an interesting concept, and the reason it is one of the exercises that I recommend you do as you watch this video, if you're taking this as part of the course, there's an exercise assigned at this point to calculate this for the synchrotron case. I'll get to that in a second. The reason this source function is so important is because you can see from this expression that as the light propagates through a medium, the intensity converges to the source function. To see that, note that you can see it this way. So let's make a little plot of the intensity as a function of distance through a medium. Sorry, I meant to put distance on this axis and the intensity on this axis. And so if let's say the source function has let's say it's a uniform medium, the source function is the same everywhere for simplicity, and let's say it is equal to this value. And you can see that the source function and the intensity have the same dimension, so I can put it on this plot, right? So that's convenient. So let's say the source function has this value everywhere. If the intensity starts off at the edge of this medium less than the source function, so I nu starts off somewhere over here and it's less than S nu, then this is positive, and this increases with distance. If the intensity starts out larger than S nu, then you can see that this is negative, and so the intensity decreases. And you can in fact see that as the light ray propagates, the intensity will converge to the source function. And so that is the reason that the source function is so important. It's important to know about a medium because it tells us for a sufficiently optically thick region, for a sufficiently opaque region, the light that we see corresponds to the source function or whatever it is that is doing the radiation. This is a fundamental concept in astrophysics and radiative transfer, and it's a fundamental concept that will help us understand every single aspect of radiation in astrophysical systems, from spectral line formations in stars, how the sun gets its Fraunhofer lines, to radiation from accretion disks around black holes, to our specific case of synchrotron radiation. So that's just a little refresher on the radiative transfer equation. And most importantly, I wanted to introduce to you here the concepts of the absorption coefficient and the source function, which you may or may not have seen before. So in the previous discussion on the synchrotron spectrum, we have derived the J-sin, which is just this J nu, and here I've written it in terms of omega, but again, this omega is just proportional to nu, right? So I may go back and forth between omegas and nus, but just keep in mind that it's the same thing with factors of 2 pi. So we've talked about the J part of synchrotron radiation. Now we're going to talk about the alpha part of synchrotron radiation, and that is synchrotron self-absorption. So physically speaking, what is going on? We have light that is propagating through a region of space. There are particles and magnetic fields that are producing synchrotron radiation through this J, but then some of those photons can get absorbed by the electrons in the presence of magnetic fields, and the electrons get accelerated and they absorb the photons. So it's just the inverse of the synchrotron radiation process. Just like you can, electrons in the presence of magnetic fields make light, electrons in the presence of magnetic fields can absorb light and become more energetic. And it's literally just the time reverse of the radiation process. So every such physical process will have such a time reverse process as well. And that's the corresponding alpha. It's the likelihood of a photon getting randomly absorbed by an electron as it's just going by merrily minding its own business. So what is the alpha for synchrotron radiation? And here I'm not going to derive this. There are derivations given in various books. I'm just going to write the expression for alpha. So the alpha nu for synchrotron radiation looks like this. It is proportional to the number of particles that are living in the region of space times something that depends upon the frequency. And now I'm just going to write it in units of frequency, but it's just, in terms of frequency, but it's the same concept regarding frequency versus omega. So it's nu to the minus 5/3 b sine alpha for nu much less than nu1, the same, where nu1 is just omega 1 here. And it is nu to the minus p plus 4 over 2 times b sine alpha to the power of p plus 2 over 2. And this is for the regime nu1 much less than nu much less than nu2. So the absorption coefficient, this is the frequency dependence of the absorption coefficient. The more particles you have, the more absorption you have. And then in terms of the frequency dependence, this is for nu less than nu1, it looks as nu to the minus 5/3. And then in this range between nu1 and nu2, it looks like nu to the minus p plus 4 over 2. And in this range, it is not really relevant because the radiation is falling off exponentially anyway. And so there, we just get this exponential cutoff in the spectrum at the end of the day. So now, at this point, I have a couple of questions for you. The first question is, what does the source function for synchrotron radiation look like? Right, so now you have the pieces to calculate it. You have J nu, in omega terms, but it's just J nu. And then you have alpha nu. And of course, there are different regimes, right? So there's the less than nu1 regime, there's the between nu1 and nu2 regime, and so all you need to do is take the ratio. So feel free to pause this video at this point and calculate for yourself the S nu in these different regimes. And then the slightly harder question perhaps is, does it make sense? Do the values of S that you get make sense? And don't worry about it, we'll discuss those after you've had a chance to look at them. Right, so we've calculated these source functions, and so let's write them down. So in the regime that nu is much less than nu1, we have our S nu, which is just J nu over alpha nu, is proportional to, so J nu looks like nu to the 1/3, and alpha nu looks like nu to the minus 5/3, and so this is simply just proportional to nu squared. And that will start looking familiar to you. Where else do you get nu squared in astrophysics? We'll come back to that. In the regime that nu1 is much less than nu is much less than nu2, which is this Paolo regime here, where you're over here. In that regime, our S nu again is this ratio, and it is, so S nu is J nu over alpha nu is proportional to now that, so nu to the 1 minus p over 2 divided by nu to the minus p over 2 minus 2. So this is half minus p over 2, and this is minus p over 2 minus 2. And so the p parts cancel, and you'll get nu to the 5 halves, nu to the 5 half power. And so that's the source function in that particular part of the frequency space. So this is now a frequency dependent source function. The source function is not constant at all frequencies. It depends upon frequency. Another cool thing to keep in mind at this point is that this source function is not the Blackbody function. So the fact that the source function doesn't look like, well, looks like a Blackbody here, we'll get to that, but here it doesn't. This is the Rayleigh-Jeans tail of a Blackbody, but this isn't, right? This is some other random power law. And so that is a critical sign of what is called a non-thermal radiation process. So a non-thermal radiation process is one where the source function is not the Planck function. And here our source function is not the Planck function, it is this power law. And that comes about because of our distribution of particles is a power law. Okay, so that's about the source function. Now let's see how this actually manifests itself. And the answer to that is from this insight we have here, which is that the intensity converges to the source function at high enough optical depths. So that means that if the system is optically thick, if it's opaque, then the intensity is going to be given by the source function. And that literally tells us the spectrum. It just tells us that the spectrum at frequencies that are at which the source is opaque look like this or this, depending upon which spectral regime you're in. Right, so isn't that neat? So literally we don't need to do any detailed integrations. You can if you want to get the full normalizations, but it tells you the shape of the spectrum. So what this means is that this spectrum isn't the full story, because at some frequency the system becomes opaque, it becomes optically thick, it starts absorbing its own radiation, and at that frequency the spectrum changes. And you can see this from here, that as you go to lower frequencies, this absorption coefficient increases, right? So there are negative powers here in both cases. So as you go to lower and lower frequencies, the absorption is higher, and so that the transition from transparent to opaque, or more kind of jargon terms, I guess, from optically thin to optically thick, happens at low frequencies. So as you go to lower and lower frequencies, at some point the system becomes opaque, becomes optically thick. The spectrum, instead of looking like that, starts looking like this. Observationally speaking, this sort of thing typically happens at radio frequencies, but it can also happen at higher frequencies depending upon the system you have. So what does that look like? So the spectrum then, in that case, will look like this. There is, so I'm just going to draw it here. So our spectrum, and let's call this I of omega to indicate the emergent intensity. It's not quite the intensity, it's the power, but let's not worry too much about it, as a function of frequency. And again, this could be I nu, which is nu, same thing. So we have, at low frequencies, the spectrum looks like nu squared, or omega squared. And then at some frequency, it transitions to an omega to the 5 halves. And then at some point, the system becomes optically thin, and the spectrum starts falling off as omega to the 1 minus p over 2, which is this segment here. And so this frequency here is omega 1. This omega 1 here. And then this frequency where the spectrum turns over, we call omega A, or omega SA, the self-absorption or the absorption frequency. Now, it may not be entirely clear why this break happens at omega 1 or omega C of gamma 1, and why this came about. And so that's what we're going to look at in just a second. So another way to think about what is going on here is that there is a characteristic for each of these electrons out here in this distribution. They have a Lorentz factor, right? So that tells you their energy. And the energy, of course, is gamma mc squared. You can define a characteristic temperature for each of those electrons. And so you can define a temperature based on writing let's put it over here, kT is of the order of gamma mc squared. So this defines the temperature scale for those electrons of Lorentz factor gamma. This doesn't mean that it's a thermal distribution of particles. It just means that this is a corresponding, it's like a relativistic temperature. It's a temperature that the particles would have had if they were a thermal distribution, roughly speaking. Now, the key thing to keep in mind is that radiation, this is a fundamental physical principle. You can never get more radiation out of a system than the Blackbody spectrum at that temperature, at a corresponding temperature at that frequency. We'll come back to this if that statement isn't clear to you. So in other words, the observed spectrum at a given frequency, I nu, is going to be the Blackbody spectrum, or the effective Blackbody spectrum, at the temperature corresponding to the Lorentz factor of the electrons that are radiating at that frequency. So in other words, these electrons have an effective temperature, right? It's this gamma mc squared over k. Corresponding to the temperature, there's a Blackbody curve, because remember, a Blackbody curve is a single parameter function of family of curves. It only depends upon the temperature. So once you determine the temperature, once you define or prescribe the temperature, the Blackbody curve is set. So for these electrons, there's a single Blackbody curve. These electrons can never radiate more light than the Blackbody radiation at the Blackbody function, or the Planck function, at a given frequency. And you can see here that we say that the radiation spectrum is omega to the 1/3 from these electrons. But you can see that the Blackbody spectrum at low frequencies, which is just 2 kT nu squared over c squared, this is just Rayleigh Jean's law, at low frequencies, rises as nu squared. So at some point, that Blackbody curve is going to intersect with this omega to the 1/3 tail, because the Blackbody curve is rising more steeply. And so you can never get more radiation than that Blackbody curve. And for that reason, that Blackbody curve is going to come and cut off the radiation spectrum. And that's where you get this nu squared from. So that is one thing to keep in mind. And so that's where you will get this region from. Where you get this omega to the 5/2 from is from noting the fact that this temperature depends upon the Lorentz factor of the electrons. Right, so each electron here has a different Lorentz factor, and so it has a different temperature. So this temperature is frequency dependent. What does that mean? So when we put in here the fact that this temperature, so this is proportional to T nu squared, and then this T is proportional to gamma, because T is proportional to gamma, times nu squared. And I'm going to just write that as gamma of omega times omega squared. Nu and omega are related. And this gamma is now the Lorentz factor of the electrons that are radiating at that frequency omega. Remember this connection between omega and gamma. And so because this gamma is proportional to omega to the 1/2 power from here, that is why you have an omega to the 5/2 power. So the radiation spectrum converges to omega to the 5/2 as long as you are in the regime where the radiation is being self-absorbed in this power law region. Let me put it this way. So you had a power law here, right? You had a power law that went up as 1 minus p over 2, and it went up until it reached omega 1 here, and then you had the nu to the 1/3 tail. But in this region between omega 1 and omega a, but instead what is happening is that at omega a, the system becomes optically thick. So this is the tau equals 1 point. And here, so let's draw a tau axis. So here tau equals 1, and here tau is greater than 1. So here the system is opaque or optically thick. And so in this region, between omega 1 and omega a, these electrons are absorbing their own radiation through this process. And because of that, the maximum intensity you can get out depends upon, is given by this Planck function at a temperature that corresponds to the temperature of the electrons that are radiating at that frequency. And so that is why, that are absorbing the radiation at that frequency. And that is why this spectrum turns over and you get to the 5/2 power. And then why do you have an omega squared at this end? That's because the radiation that is being emitted here, it comes from these omega 1 electrons. And so all of this radiation was produced by this omega-1 electrons. And in this region, those electrons are absorbing their own radiation. And so now in this region, the temperature is no longer frequency dependent. The temperature is just the temperature of these electrons, because that's what is absorbing the light here. And so the temperature is now constant, and so there's no, in that region, the temperature we use is just gamma 1 mc squared, not gamma mc squared. And so in this region, the relevant I nu is just proportional to nu squared or omega squared. So that's how this works out. And so feel free to, at this point, pause this video and see if you understand what we just talked about and how the radiation spectrum gets self-absorbed and results in these two power law segments. I know we just talked about a whole bunch of different things, from the radiative transfer equation to the conversions of the intensity to the source function, the expressions for the source functions in different regimes, and how you can see now the intensity is converging to the source function in these regimes. And then we discussed a kind of a, let's say, physical insight type of way where we try to understand why that is happening. And that's because the intensity can never be more than the Planck function at a given temperature. And so we defined a characteristic temperature for each electron, and that helps us understand this. So feel free to pause this, and I'm going to connect these two in a second. Right, so this particular distribution, or this particular shape, requires the optical depth to be unity above omega 1. But it is also possible that the system is, the density of the system is low enough such that the system doesn't become optically thick until you are at lower frequencies. And so if you go in the direction of, let's say, decreasing density, then the spectrum can look slightly different. And so there you could have the case where we have our omega 1, and we have our omega A is actually less than omega 1. And in that case, the spectrum here is going to look like nu squared, because that's self-absorbed. But then what happens above it? And this is a question for you, so feel free to take a moment to think about what happens here. So you can pause this video if you haven't already and see what happens. So right, so we have our nu squared segment. And then over here, in this region, the system is no longer optically thick, and so you return to this the spectrum that you were expecting. So you get a, let me make this even steeper so it's clearer, the contrast is clearer. So we have a nu squared, then we have a nu to the 1/3, and then we have a nu to the 1 minus p over 2 segment. And this will continue all the way up to nu 2, which is not directly relevant to this discussion. So here, this system, the tau equals 1 point is over here. This part is optically thick. This part is and above is optically thin. If all of this is confusing to you, if it doesn't make sense, another way to think about this is looking at this plot, right? So think about, let's think about this and try to understand like what we discussed here. So we had this spectrum, which we understand as just as JSIN. Each of these electrons has a corresponding temperature. For the radiation over here, the relevant blackbody temperature is that for the electrons that are radiating at omega 1. So these guys at omega 1 have a corresponding blackbody function, and that blackbody function sits somewhere, I'm going to draw it as a dotted curve, sits somewhere up here. At very, very high energies, this will fall off exponentially, and it'll cut off the spectrum. But at that point, we're already falling off because there are that's going to be at a much higher energy. The most visible effect of this blackbody is this nu squared Rayleigh-Jeans regime. And so because you can never get more radiation than this blackbody function, and so this blackbody function corresponds to electrons that are radiating at omega 1. It's these gamma 1 electrons, their blackbody function. And so this blackbody function comes and cuts off the spectrum at these low frequencies. And so this is the point at which the flux that you would get from the synchrotron spectrum equals the Blackbody's spectrum that you would get from these electrons if they were radiating thermally with that energy or with that Lorentz factor. Right, so this Blackbody function is the radiation they would produce if they were at that temperature. The synchrotron spectrum is the radiation they're actually producing at low frequencies. The synchrotron spectrum says, I want to produce this much light, and Blackbody spectrum says, no, you can't do that, you can't produce more light than me, and so that's why you get this nu squared segment. That's another way to think about this. And so this is another reason why sometimes one of the ways this self-absorption frequency is found in astrophysical situations, it's calculated, is by equating the Blackbody spectrum for that relativistic temperature to the flux that you would get from the synchrotron spectrum. But a proper way to do it is to actually calculate the location or the frequency at which the optical depth is unity. In this case, you can use the same argument. And in this case, what is happening is that you have a series of these Blackbody curves. And now the Blackbody curve is different for each of these at each frequency over here, because it corresponds to absorption by different electrons. And every electron at different Lorentz factors has its own absorption coefficient. So this brings us to the end of our discussion of synchrotron self-absorption. It may feel like a lot, especially given that there are lots of different aspects going on here, from the radiative transfer equation to absorption coefficients to this Blackbody maximum efficiency thing we talked about. But the thing to keep in mind is that synchrotron self-absorption steepens the spectrum at low frequencies. It can result in a nu squared nu to the 5/2 or nu squared nu to the 1/3 transition, depending upon at what point in the spectrum does the radiation become optically thick, at what point does the radiation start becoming self-absorbed. And as you can see from this is an example of a density tracer, because if your spectrum looks like this, it's probably higher density. If your spectrum looks like this, it's probably lower density. And so the self-absorption frequency is a very strong, has strong dependencies on the density, and the shape of the spectrum also tells us something about the density. So this is an excellent way of learning something about the density of the system we're looking at. So harken back to the very first video of this series where we discussed what are some things to keep in mind when talking about new radiative process. And we said we want to know what it is, we want to know where it is found, we want to know its equations, we have so many equations. And we also want to learn something about how we can learn, we can learn about the universe using those equations. And so we haven't necessarily done that as we've gone through, but here's an example of how you can learn something about, in particular, the density, for example, of the universe, or a particular radiating part of the universe using synchrotron radiation. So after this, there's one more element I'd like to talk about in the next video, which is the aspect of synchrotron cooling. But feel free to kind of scrub through this and look at various aspects of synchrotron self-absorption until you feel you're comfortable with this phenomenon.